This lecture is going to be about the compression and expansion of gases, looked at from the point of view of thermodynamics. It's a very, very important subject from a practical point of view because there are so many different applications. For example, your motorcycle engine or your car engine works on the principle that some gas is heated, then it expands, pushes against a piston, the piston does work. The same holds true for a jet engine, which pulls in cold air, heats it up, throws it out at a very high velocity. But it's not just here on Earth that thermodynamics finds application. In the skies, there are stars which are burning, and inside them, it's gases which are pushing, which are getting heat pumped in, and also releasing heat. So we need to understand the behavior of gases and to an extent fluids. Well, fluids are somewhat less compressible, but we need to understand all these things to understand natural phenomena. In fact, even to understand the Big Bang in detail, because there was a photon gas which was pushing against the matter outside. So let us begin with some general principles. Let me begin with something that is very general. Every thermodynamic process is either reversible or it is irreversible. By a reversible process, I mean this system can be of gases, solids, whatever, electrons. The system can go from some initial state, so for a gas that would be just the pressure, volume, and temperature, to a final state, and then we can take it back to the initial state by slowly reversing in time. What that means is that you can make a video of the system going from the initial to the final state and then back to the initial state. And then if you reverse the video, you will not be able to tell which is the reversed one as compared to the original one. At every stage, this system is in equilibrium. So that means that one is going very, very slowly. The pressure, volume, temperature, etc. change so slowly that at every instant of time, the system is in equilibrium. Now, this means that this is going to take a very long time, in fact, an infinite amount of time to go from the initial to the final state. And of course, this means that there is no such thing as a perfectly reversible process. Actual physical processes are in fact never exactly reversible. Now let me illustrate what I mean. So here is a system. That system is a gas with a piston with a weight on top. Now this gas is pushing upwards. The weight is forcing the piston downwards, and if the two forces are exactly equal, then there will be equilibrium. However, if I move a little bit of weight to the left over here, then the force here will be greater than the force here, and so this piston will move up slightly. Now here, a little more weight has been moved, and so now the gas has expanded. Now these weights are very, very small, so in going from this state, pressure, volume, temperature, to this state, pressure, volume, temperature, has taken a very long time. We can remove more weights and finally reach the maximum extension and arrive at this state, and then slowly add them back. So now this state is the same as this state, and finally we get back from here to here. This has taken a very, very long time. Imagine that you had made a video of this process, going from here through these stages and back to here. If you had run this video backwards, you would have not been able to tell the difference between the original and the reversed video. So this is what I mean to say that this process is reversible in time. Now here are 4 examples of irreversible processes. So take a gas that is confined to this part of the box. This part is empty. Let's say that they have equal volume. Now I remove this partition that is separating the 2 boxes, and so the molecules of this gas spread out, and soon you will see an equilibrium situation where the molecules are more or less uniformly distributed in the box. If you were to make a video of this, certainly you would see it going in this direction, and if you ran it this way, you would know that the video has been run in the wrong direction. You can never go from here to here. Similarly, if I have molecules that are blue and molecules that are red, and I remove this partition, you know that this will go towards this situation where the molecules mix with each other, and that this can happen only in one direction, not in the other direction. Here's another example. This is sodium chloride or some substance that dissolves in water. When you put it in water, the bonds are weakened, and so this crystal over here then spreads out, the atoms get uniformly distributed, and this can happen only in this direction. You never see a glass of water like this in which this spontaneously drops out and creates a crystal. As our third example, suppose we have a box like this. There's air, a hot stone, and ice. After some time goes by, the ice melts, the stone becomes colder, and the air is warmer. Soon they will be at the same temperature. We know that this is the way that things naturally happen. A video made of this system would tell you that this is the proper direction of time. And finally, suppose that I take some dye and put that dye at the bottom of this beaker. After some time, the dye molecules spread out and the whole glass becomes red, and again there's a very definite direction to time. You know that this does not ever change back into this. Of course, all physical processes are actually irreversible, but it is useful to think of reversible processes. They are idealizations, very much like the idealization of a free particle. In nature, there is no such thing as a free particle, but still it is very helpful to think of a free particle. In fact, you cannot even begin doing classical mechanics without that concept. In thermodynamics, reversible processes are important for the same reason. Now let's look at the expansion of gases, and I will consider 4 different cases. The first case will be that of a reversible expansion. This will be isothermal. Iso means constant, and this means temperature. So this thermodynamic change will occur at constant temperature, and the system will be a closed system. So for example, over here, this is a gas that expands from some volume, let's say below this, to some final volume. This transformation happens reversibly, which means that in going from here to here, the system is in equilibrium at every point. It is a closed system, by which I mean that no molecules of gas are allowed to leave or enter inside over here. And now, to be more definite, let's assume that this is an ideal gas. Ideal meaning that the molecules don't collide with each other, and this obeys PV equals NKT. So this ideal gas expands from volume V1 to volume V2, and the temperature is fixed. So the walls of this container are at fixed temperature. We are asked to find the work done by the gas. This is just to repeat that the ideal gas has got PV equals nRT, N is the number of moles. And now you know that the work done by the gas is dW equals PdV. Let's be very clear that in expanding, the gas is pushing upwards, and this piston has moved a certain distance up, which means the gas has done work. Now the force into the small distance is really this PdV, because P is force over area, whereas dV is area into the small distance moved. So the work done by the gas is dW equals this. Now this is the small amount of work done. The full work done is got by integrating PdV. P is not a constant. You can see from here that as V increases, P decreases, and so you must do an integral. That integral is just integral of dV over V, which is the logarithm of V between the limits V2 and V1. So that's log of V2 minus log of V1. But you know that that is the logarithm of V2 divided by V1. And that is the work done by the expanding gas. Next, let's find the heat put into the gas. So you see over here that this gas was heated. So an amount of heat delta Q was put into it, and this is what enabled the piston to do work. The first law of thermodynamics tells us exactly how this happened. Well, the first law says that the increase in the internal energy is equal to the heat input plus the work which is done on the gas. So this capital W is work done on the gas. The work done by the gas, therefore, has a negative sign. Now let's realize that the internal energy is a function of the temperature only. In fact, you remember that U of T for an ideal gas is just 3 over 2 nKT. Since we are holding T constant, therefore, there's no change in the internal energy. And therefore, dQ and dW are exactly the same, which means that when we integrate dW, we get the total heat that has been put in from the outside is equal to the total work that has been done by the gas. Nothing is surprising over here. The internal energy has not changed, and so therefore all the heat that you put in was converted into work. This was for an isothermal change in this closed system. Now let's go to a different situation where again we have a reversible change, but this is done under constant pressure. So again, iso means constant, bar means pressure, and now imagine that in going from here to here, the pressure that is exerted on the piston is constant. To be more definite, this ideal gas expands from V1 to V2 at fixed pressure, and the initial temperature was T1. I'm not saying that the final temperature is T1 also. This is not isothermal. The temperature will change. Now let's find the work done by the gas. Again, we have the small amount of work done as P times the change in volume. And so, since P is constant, this integral is very easily done. You do P dV from V1 to V2. P is a constant, so you pull it outside, and so you simply get V2 minus V1 times P is the work done by the gas. You can write this in a slightly different form because PV is equal to nRT. So P into V1 is equal to nRT1 and P into V2 is equal to nR into T2. So this W can simply be written as nR into the difference in the temperatures. Now we are asked, find the change in the internal energy of the gas. You see, the temperature has changed, and so the internal energy has changed as well. For the ideal gas, as was discussed in a previous lecture, the internal energy is 3/2 into nRT. This is for a gas that has simple atoms or simple molecules that can simply move in the x, y, or z directions and no rotation is possible. U is this, and so du, the small change in internal energy, is just proportional to the small change in temperature. On the other hand, P dV, we can see from here, remember that P is a constant, so P dV is equal to nR dt. And so therefore, the change in the internal energy du from here, or rather from here, du is the same as 3/2 P dV. Of course, you can integrate this. Since P is a constant, then the integral of V is just V itself, and this is between the limits V2 and V1. So the finite change in the internal energy is 3/2 P into V2 minus V1. What about the heat input? Well, that's easily done using the first law of thermodynamics. Now here, remember that dW is the same as minus P dV. So dQ is equal to du plus P dV. So that means that the total heat input is equal to the increase in the internal energy, which is this, together with the work done by the gas. And that we have calculated earlier, which is over here, P into V2 minus V1. And so the amount of heat that you needed to put in is 5/2 P times the difference in the volumes. This makes a lot of sense because the amount of heat that is put in is equal to the work which is done by the gas plus the increase in the internal energy of this gas. Let's go on to the third case. And this will be, again, also reversible, but it will be adiabatic. Adiabatic means that no heat is allowed to enter the gas or leave the gas. So you can think of these walls over here as being perfectly insulating. To be more definite, consider an ideal gas which goes from a certain volume V1 to another volume V2, but this time without exchanging heat. In both the previous examples, we had allowed heat to enter the system. Now there will be no heat allowed. First of all, we are asked to find the equation obeyed by the gas as it expands. Now remember, as it expands, its temperature is not going to remain constant. So let's begin with the first law of thermodynamics again, which says that du is dq plus dw. There's no heat exchange allowed, and so du is equal to dw. dw is the work done on the system, which means that du is equal to minus P dV. As this piston goes up, it's doing work. Where is the work coming from? It's coming from the internal energy. That internal energy is decreasing as the piston moves up, and this is what this negative sign is telling you. So as the volume increases, the internal energy will decrease. To say this again, the ideal gas has got U, which is 3 over 2 nRT, but PV is equal to nRT, so U is equal to 3 over 2 PV. And now, let's look at U equals 3 over 2 PV and imagine small changes in P and V. So du will be 3 over 2 P dV plus V dP. Effectively, what we've done is we've changed P to P plus dP and V to V plus dV, and then thrown away the dP into dV term. So the small change in the internal energy is this. This 3 over 2 is for a monatomic gas, one that cannot rotate, and we could be more general and call this alpha. If the gas molecules can rotate, this will be not 3 over 2, but 5 over 2 for a diatomic molecule. It'll be different for more complicated molecules. Let's just call this alpha. So then, let's look at this equation. In this equation, I put du equal to minus p dv. And then, from here, du is alpha into p dv plus v dp. Simplify this a little bit by taking dv on the other side, and so we get minus alpha plus 1, p dv is equal to alpha v dp. To simplify this, let's divide both sides by p into v, in which case we get alpha plus 1 dv over v plus alpha dp over p. And now, again, do another simplification. Define alpha plus 1 over alpha as gamma, and this gamma is just, as we see, 3 over 2 plus 1 over 3 over 2, which means 5 over 3, and this is the ratio Cp to Cv as we had derived earlier. So now, in this equation, I have divided by alpha, and so I've got a gamma over here instead, and this alpha has gone away. That means I get gamma into dv over v plus dp over p equals 0. So this is relating small changes in p to small changes in v. Now this can be easily integrated. When I do the integral of dv over v, I'm going to get log of v. When I do the integral of dp over p, I'm going to get log of p. And so, this equation becomes gamma log v plus log p is equal to some constant. You can check that very easily. Just take the derivative. So I would have gamma dv over v plus dp over p equals 0, because the derivative of the constant is going to be 0. On the other hand, I can write this gamma log v as log of v to the power gamma. And then I have log of v to the power gamma plus log of p, which means log of v to the gamma multiplied by p equals some constant. In other words, log of pv to the gamma is equal to some constant, and that has given us a very important relationship. Pressure into volume to the power gamma, and this gamma is the specific heat at constant pressure divided by the specific heat at constant volume, that PV to the gamma is always going to be a constant. Now this means that, let's say over here the pressure was P1 and the volume was V1, then P1 into V1 to the power gamma will be unchanged when this gas expands and occupies a different volume, and there it will have a different pressure, but P1 V1 to the power gamma will be P2 V2 to the power gamma will be whatever, P3 V3 to the gamma, etc. The point is that this is the equation obeyed by a gas when no heat is allowed to be exchanged. Remember, this came from the equation PV equals NKT, but we have allowed now T to be changed, and so PV is not a constant. It is this quantity which is a constant. You can ask, how does the temperature change? So let's now continue this expansion. So this ideal gas is going from V1 to V2 without exchanging heat, the same as before. If the initial temperature is this, what is the final temperature? And now that's very easily done. We are using the ideal gas law. We use this to derive PV to the power gamma is equal to a constant. Okay? Now, instead of P, I'm going to put nRT divided by V. So nR T1 divided by V1 into V1 to the gamma. Now this has to be the same with the temperature being T2, the volume being V2. And so we now have a relationship. You see, N and R cancel over here. What is N? N is the number of moles, and we are not allowing any changes in the number of molecules, so they cancel from both sides. And so we get the relation between the temperature and the volume. Earlier, it was the relationship between the pressure and the volume. Now it is between the temperature and the volume. And you can see that this gamma minus 1 came because there's a V1 in the denominator. Okay, let's work out an example. So there's an ideal gas which is initially at 0 degrees centigrade. 0 degrees centigrade means 273 degrees Kelvin. We are asked to find the final temperature when the volume increases 10 times, reversibly and adiabatically. Again, this is to be done very, very slowly, and adiabatically means no heat is allowed to enter or leave. So T final into V final is equal to T initial into V initial. That means that TF is this. Now, the final volume is 10 times the initial volume. The initial temperature is 0 degrees centigrade, which is 273 degrees Kelvin. Just use a calculator. You'll find that this is 59 degrees Kelvin, which means this gas has cooled down to minus 214 degrees centigrade. If it's cooled down, that means this gas has lost internal energy. Why did it lose internal energy? Because it did work. When the volume expanded 10 times, that means work had to be done against the piston, and that caused the internal energy to decrease. As the fourth and final case, let's take the irreversible change, this time note irreversible change, in this closed system. So you have an ideal gas which has some volume, V initial. It's at 0 degrees centigrade, and we are asked to find the final temperature if the gas expands suddenly to 3 times its volume. So imagine the following. You have gas which is confined over here, and then suddenly you remove the partition, and so the gas spreads out. This is irreversible. What do you think will be the final temperature? Now, when I took away this partition and this gas spread out, there is no piston. And so no work was done, no heat was put into the system either, which means that the internal energy of the gas did not change. We arrive at the conclusion that there's no change of the internal energy and so no change in the temperature either. Finally, let's look at an application of the ideas that we've so far developed. We will look at the speed of sound. Now, sound is emitted from some source, in this case, this loudspeaker. The diaphragm of this loudspeaker goes back and forth, and so it creates fluctuations in the pressure of the air between the source and where it is received. So let's solve the following question. We are given that the speed of sound v is the square root of this quantity. This is the derivative of the pressure with respect to the density of air. Here, P is the steady pressure and rho is the steady density, meaning that these small fluctuations of pressure and density are because of this loudspeaker. Turn off this loudspeaker and what you would get is the ambient or the steady pressure and steady density. We're given this formula. I'll just explain how it could be derived. We are asked to find V assuming that the air undergoes compressions and rarefactions that are either adiabatic or isothermal. I'm not going to derive this formula, but intuitively, the stiffer the medium is, the greater is the restoring force, and the faster a wave will propagate through a medium. So here we're looking at how the pressure changes when we change the density. If we change the density only a little bit, but the pressure changes a lot, then V is going to be greater. And in fact, you can see that in iron, for example, if you were to compress the iron, you'd make a small difference in the density of the iron, but you'd make a lot of difference in the pressure. And so the speed in iron would be greater than in air. Now here you can see everywhere that there's compression here, 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 and here. And there's rarefaction here, 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 and here. But is this compression of the gas adiabatic or is it isothermal? Let's work out both cases. Let's take the adiabatic case first. So pressure into volume to the power gamma, and this gamma is Cp divided by Cv, ratio of the specific heats of air. This is a constant. If it's a constant, that means if I differentiate both sides, then the left-hand side will be something, the derivative of the constant will be 0, and if I take the derivative of this is dp v to the gamma plus p into the derivative of v to the gamma, which is this, and that's equal to 0. Simplify this a little bit by dividing by p v to the gamma, and so this equation becomes dp over p plus gamma dv over v. That immediately tells us that dp by dv is equal to minus gamma p over v. But remember, we don't want just dp over dv, we want dp by d rho. Now if we use the ideal gas law, P is proportional to 1 over V, then obviously dP by dV from here will give me this, a negative sign because this is V to the power minus 1. Now obviously if I put P over here, then I get dP by dV is minus gamma with a V squared at the bottom. However, what we want is not just dP by dV, we want the derivative with respect to the density. So, suppose there are n atoms in this volume V and each of those atoms has got mass m. In that case, the mass density is the total mass, which means the mass of each atom into the number of atoms divided by the volume. So now we have rho is proportional to 1 over V. In that case, we can take the derivative d rho by dV, and that's obviously just minus 1 over V squared into m into n. Now use the chain rule. Remember that what we want is dP by d rho. Well, dP by d rho is dP by dV into dV by d rho. We already have d rho by dV, and this is just 1 over that. Put this in, and we get minus gamma P over V from here. We multiply this by 1 over this, which means we have a V squared here, Mn here, and now just put P equal to NKT divided by V. So we're going to get a V squared in the denominator, which will cancel this. The n's will cancel, so this n and this n will cancel. And so we get simply that dP by d rho is this quantity, gamma Boltzmann constant into the temperature divided by m. And so now we have the speed of sound, which is dP by d rho. This was for the adiabatic case, of course. And now let's go to the isothermal case. Well, in the isothermal case, it's very simple. It's even simpler because PV is equal to a constant. Remember, isothermal means T is a constant. Now this means that we don't have to repeat everything above over here. Simply put gamma equal to 1. So instead of PV to the gamma as a constant, PV is a constant. That means we don't have to do any more work. The speed of sound V in the isothermal case is simply got by putting gamma equal to 1 here, and we have square root of kb into T over m. How does this work in practice? Well, the measured value of the speed of sound at 0 degrees centigrade, which is 273 degrees Kelvin, is 344 meters per second. Does this work well or not? Let's look at the isothermal case first. So this is 283 meters per second compared to 344 meters per second, which is not very good. If I take the first case, the adiabatic case, and I put in the value of gamma as being approximately 1.4, so this is the ratio of the specific heats of air at constant pressure divided by constant volume. Experimentally, this is found to be 1.4. If I put that in, and in place of m, I put in the mass of a nitrogen molecule, and that's because most of air is nitrogen, then I get that the speed of sound is 335 meters per second, which is not exactly 344, but it's certainly a lot better than 283. And that tells me that sound waves are more adiabatic than isothermal. In other words, heat is not entering or leaving these regions where there is maximum compression or rarefaction. The actual thermodynamics of sound is a little more complicated. It is mostly adiabatic, but there is also heat loss in the isothermal case. However, this is as far as we are going to go. We have learned a lot just by considering these ideal gases and the nature of adiabatic and isothermal expansions.